I've got this nice analog power supply, this old-fashioned transformer power supply that came out of some audio equipment, some dead audio equipment. But this is a nice power supply. It's, you know, it's very heavy, obviously, but it's, you know, it's got a good range of voltage. It says 2 times 19.5 volts AC up to 1200 milliamps. So I'm thinking this could be quite a good power supply to have around for maybe for creating a split rail power supply for testing audio stuff. So what I was going to do is you build a bridge rectifier for this and do some maths and show how you do the calculations for converting from AC to DC, and so I'll go through a little bit of a design workshop. Now first I wanted to actually measure the voltage that's coming out of this guy. So I don't think there's any active circuitry in here at all. I think it's just a big transformer. So it's got this 3-pin connector, and I've got the other end as well. I've got the socket out of the equipment, so I'm going to reuse that. So if we have a poke around in here, I've set the meter to AC because this says that it's got AC coming out of it. And if I put the negative in the center pin there, so we got 21 volts AC on one side, just a little under 21 volts on the other side. So I think it's a center tap transformer. If I put the probes across the other two there, so yeah, so we get nearly 42 volts across the whole thing. So what I think we've got here is a big center tap transformer like this. So we've got 21 volts over one side, 21 volts over the other side, and then all three of these come out to the connector. So to build a DC power supply out of this, you need a bridge rectifier. So what I intend to do is I'll connect the end ones up to a bridge rectifier here. I've got some nice bridge rectifiers here, so I'm going to take one of these. Let me show you. So this is a nice 4-pin device. I've got a few of these. These are 2 amps. So they should be able to. They should be suitable for a power supply that's got a 1.2 amp output, and that's got the 4 diodes inside, which is very convenient. Makes it easy to build a circuit. So if I've got the so I want 2 coming out like this. This is going to be my plus, this is my minus, and then the diodes inside. The diodes are going to point that way. So you got AC coming in at the top and bottom, and then you got plus and minus coming out here. And what I'll do is I'm going to call that center tap ground, and then here what I'm going to do is I'm going to call this my plus V, and I'll call this my minus V, and these will all be relative to that ground. So then we're going to put some smoothing capacitors here, because the DC voltage coming out of here still looks a bit choppy, so we'll put a couple of smoothing caps in here. And then this goes down to ground as well, so this is our 0 volt reference. What comes next, I'm not sure. I might put some kind of regulator in here. Haven't really decided yet. We'll get to that when we've figured out the maths for this here. So looking a bit at what the AC waveform looks like, we've basically got a sine wave, so a repeating wave like so. And the maximum voltage here, V peak. So VP I need for my calculations, but what the meter has told me is something called VRMS, so root mean square. So the RMS is a kind of average value, so it represents the equivalent amount of power that would be delivered if this were just DC. So that's what VRMS is. So I know the VRMS value in this case it was 21 volts. It was about 21 volts. So using that I can work out what V peak is, because I'm going to need that in a moment. So in fact, as it turns out, VRMS is equal to V peak over the square root of 2. So this means that in this case we can, well, so if we rearrange that, we get VP equals root 2 times VRMS. So here we've got 21 as our VRMS. So if I multiply that by the square root of 2, there we go, I get 29.7 volts. So here my V peak will be 29.7, which is quite surprising when you see it, because the peak is obviously much higher than the VRMS value. So why do we need that? Well, the next step, when we put this through a full wave rectifier, what happens is that all of these negative peaks here also become positive peaks. So we've got this instead. So that's the magic of the full wave rectifier. Again, well, this is not quite V peak anymore. This is going to be V peak minus about 1.2, and the reason for that is because the current path is going through 2 diodes now. So if we imagine the positive cycle of the sine wave, what's happening here is that the current is flowing out through this diode here out into the circuit, and then the current is coming back, it's coming back into the back of this diode, and it's flowing through this way before it gets back to the transformer. So this diode and this diode are in the current path, and the voltage drop across a diode is about 0.6 volts in the forward direction. So you add that to that and we've got our 1.2. So we have to allow for the V peak minus 1.2 in order to understand what the shape of that waveform is. Now if we look at the average voltage, because after this goes through some capacitors, there'll be a smoothed version which will look more like direct current, and this is an average value of these humps in the sine wave, and turns out in fact that the average voltage, so V av, is 2 over pi V peak. My pen's running out. 2 over pi V peak. So we should be able to work that out. So we've got 2 over pi in this case times, well, we have to do Vp minus 1.2, so this is 29.7 minus 1.2, and that should give us our average value. So once again, 29.7, take away the 1.2 times 2 and divide by pi, and we get V average is 18, well, let's say 18.1 volts. So what I'm expecting from my power supply in this case is, you remember I've got a split rail, so with my plus V, my ground, my minus V, so I'll be expecting to have plus 18 volts on one half of the power supply, and then I'll have minus 18 volts on the other side. So that's actually quite a useful amount of voltage for doing things like driving op amps in audio circuits. So I'm now going to build something, so I'll get a few components and I'll build up that bridge rectifier, and we can actually measure the voltages in the circuit and make sure that this maths that I've done is all in fact true. I'll show you where I've got to so far. So I've chosen to use a bit of strip board. I rather like strip board, and used a drill to cut some of the tracks that I don't want to go all the way through from one end to another. And I've put my regulator on there. So I've got the two ends of the transformer coming in from my connectors here. I've got my ground, so I'm just going to do some measurements before I carry on and add the capacitors. I found some suitable capacitors that they're not exactly matched, but they'll do fine, I'm sure. So first of all, I'm going to do an AC measurement. Just measure the AC voltage coming in. We've got 40.6 there. It does vary a bit because this transformer is obviously completely unregulated. So we've got 40.6, and now we'll measure the other side of the bridge rectifier. So we've got, if I measure from plus to minus, there we've got 37.38, and if I measure from ground, so that's the positive, measure to ground, I get 18.59, and then the negative is 19.03, so 18.56, 18.6 and 19.01. Oh, it's dropping again. So they're not exactly, the two windings of the transformer are not exactly the same, but that will do. So slight change of plan. I abandoned the earlier bit of strip board because I needed a bit more space on this side, because I've decided what I'm going to put there, and I'll talk about that a bit more in a minute. So so we've got the strip board here, or the, I don't know what you call this, but it's got little sort of circles of that you can solder. So it's not really strip board, but I've got this matrix board, and I've connected up the bridge rectifier. I've got a couple of capacitors, so we can actually test the voltage now before we do any further assembly. So I plug in the power supply, and we're in the DC setting on the multimeter, so I'll just check the positive side capacitor. That's 26.5 volts, and the negative side capacitor says nearly the same, minus 26 odd volts. So that's what we've got before we do any regulation, or before we put a load onto this power supply. To talk a little bit about what comes next, what I decided to do here is to put a couple of voltage regulators on the output, and so these are the ones here. So I've got the LM317 and the LM337, and so let me describe that a little bit. So if you remember, we have the AC coming in, we have a bridge rectifier, we've got the positive side coming out, we've got the negative, and then we've got the, so here we've got the center tap, which I call ground. So let's draw that in the middle for clarity. So on the positive side, what I'm going to put here is a chip called the LM317, which is a voltage regulator, and that uses a couple of resistors between there and ground that set the voltage level. So this will probably be about 18 volts, because that's what I worked out the final voltage, DC voltage, would be from this power supply, and probably be another capacitor there to get rid of ripple and make the system more stable from oscillation and so on. And then on the negative side, you get the sort of mirror replica. So there's a chip called the LM337, which is the negative version of the same thing. So you got a negative voltage coming out of here, and so the LM337 you connect up in the same way. That's connected to ground there, but then this is giving a negative voltage relative to ground, so you need a different chip for that, but it works more or less in the same way. The pins are confusingly a different way around, but it basically works in the same way. So that's what I'm going to do basically. So you got unregulated DC on this side here, and then after the 317, 337 stage, we'll have a stabilized regulated voltage on this side. The regulators have been assembled on the board now, so you can see I've got the LM317 here and the 337, its negative counterpart here. A couple of things to mention about this. You'll notice if you look closely, there's a little sort of plastic insulator here in between the regulator and the heatsink. So incidentally, this heatsink is just one that I had in the drawer. This is off a processor, I think probably in a TV box, so like a PVR. I think that's where that came from. So I drilled a couple of holes in here, used this to mount the regulators, and so we have an insulator there, because in the case of the 317, the tab is the output from the chip, as well as being one of the pins down below. And in the case of the 337, the tab is the input. So in neither case do we want this to be electrically connected to the heatsink. So if we just screwed these down, we'd have the output here connected to the input here, and something would get very hot, I think. So we got the spacers in there, and I also put in some heatsink compound because you want a good thermal connection between the regulator and the heatsink. And there are a few other ancillary components here. So we've got the resistors that select the regulation voltage, and also some protection diodes. So there's a standard way to connect a couple of diodes just in case voltage gets put in here to stop the voltage or spikes coming back from equipment and blowing up these chips. So I just put that in to give it a bit more resilience. Incidentally, the way that the voltage is chosen by the regulator circuit, if you remember, we have the regulator in this form here, where R2 is connected to ground, R1 and R2 make a voltage divider that drives the adjust pin in the 317, 337 regulator chips. And the formula for the voltage output that comes out of that pin is now it's 1.25 times 1 plus R2 over R1, like so. Now in my case, what I did is I used a standard value for R2, which is 4.7k, and my R1 was made out of two different values that I put together to get the right combination. So I've got 330 ohms plus 39 ohms, so that gives us 369. So if we put those numbers in, we get 4700 divided by 369 gives us 12.7. So we add the 1 and times by 1.25, and we get 17 volts. So that says 17.17 volts. But there are, the tolerances of these resistors won't set the voltage absolutely accurately, but we're expecting about 17 volts. So the moment of truth, we're actually going to connect up the power supply now, connect up the transformer and see what voltages we get out. So here these pins are the ground here, so the 0 volts rail. This is the positive rail, so plus 17 volts, and this one is the negative rail, minus 17 volts. Okay, so I had some camera difficulties there. I just lost my first test of this circuit, but let's go again. So I'll test the input side. I've got the meter set for AC volts, so I've got 19 volts that side, 19 volts that side, and now we'll check over, let's switch to DC volts, and we'll now check the output. So I've got the ground there, that lower pin, so that gives me 17.6 volts, so that's a bit higher than expected, but okay. And then the other pin gives me minus 17.6 volts. So there's a good agreement between the two regulators, the positive and the negative regulators, as you might expect, because they're using the same R2 and R1 values in both cases. So that's good. So I've now got a approximately 18 volt split rail power supply, which is going to be ideal for connecting up op-amp circuits and testing things like op-amps that need a split rail power supply. Right, well, thanks very much for watching. Give me a thumbs up if you enjoy this kind of video, and please subscribe, please comment. I love to see your comments, and see you again next time in the next video.